This is part 2 on my series of celestial navigation on a flat Earth. I call it the leak sunrise method. If anybody's already done this, I apologize. Please bring it to my attention and I will get that information out there. Now, it's shown on the Gleason's map that it's a longitude and time calculator. And you see where I pointed at 12 o'clock on the right and then 12 o'clock on the left. They represent the hours and degrees of longitude. They all start at 12 o'clock. The prime meridian, 0 longitude, runs through Greenwich, UK, straight to the central pole. This is the most important category in celestial navigation, and it's not really measurements. It's degrees of longitude around the central pole. So it's 15 degrees an hour, going all the way to 359 degrees, back to 0 at the prime meridian. You hear a lot of people complaining about the angles, like especially on equinox, that 90 degrees doesn't line up. That's because they don't understand the Gleason's map and they don't understand how to use it. So I'm going to try and clear that up here, and I'll point out some of the issues with their model. Let's talk about the globe angles. Look between north and east. That represents 90 degrees. And between south and east is the other 90 degrees. Same thing in the south. So they should have to bend their north and south to accommodate these great circles. But it's confusing. So it works perfect at the equator, but then they bend their north and south. So the only place where the 90 degrees is legitimate, then they bend their horizon basically. So this is what I mean. 90 degrees at the horizon from everywhere on the equator is Polaris. So everybody's looking at Polaris, looking at the horizon from the equator. To do it correctly, they would have had a central point in the east and an antipode west, like they're north and south. Then everything would be great circles. This alone shows me they used a flat Earth map to make their model. The first thing we're going to do before the sun comes up is measure our angle to Polaris. And that's going to give us our latitude. So we're going to draw a semicircle to match our latitude. So if Polaris is just right at the horizon, then that means we're at the equator, 0 latitude. And if it measures 23 degrees or 23.4, then we're at the Tropic of Cancer. So that's where we're going to start. So after measuring our angle to Polaris, we draw it on the map as on the semicircle, and we know we're somewhere on that circle. That's our location, is somewhere on that circle. Then we go to the Nautical Almanac, and I showed it here, all the different categories. It's an enormous amount of information. It's pretty impressive, to say the least. And here we go to the sun tables, and it has all the months, days, hours, and then there's even increments with minutes and seconds. But we're just going to do the basics here. So I'm going to give an easy example. I'll go into details in further episodes, but so this is the starting with 0 hour all the way up to 23 is on the left, and then the next column is the Greenwich hour angle, which is the position it is on the circle, and then the next where you see N00, that is the declination, meaning the angle from the equator, so it's right overhead, meaning 0, and then to the right of that is the minutes of degrees. They have to call it the declination from the celestial equator because they chop their Earth in half so they can have a flat plane to work on, but it's just the declination from the equator, or the latitude. So if it were summer solstice, it would say N23, meaning the sun is over Cancer. And if it were like December 21st or the southern solstice, it would say S23, South 23, or meaning the sun is over Capricorn. So first thing we're going to do is record the time, and then we are going to mark north, and we're going to measure the angle from north that the sun rises. Now we are Central Time Zone, which is UTC minus 6, so we're going to add 6 hours, and that gives us 12, because 6 a.m. has done came and went for the UK. So if it's negative, you add the hours to it. So like I said, we're going to do the increments. I'm just trying to keep this simple. So it says 358, which means it's damn near back to 0. So it's almost at the at the prime meridian. So we're going to draw our line. I circled the time right there, 12 o'clock, and drew a line. And now 90 degrees from that is our longitude. Our longitude. We really didn't even have to draw the line. We could do it with the clock itself, but like I said, we're going to get into the details and in a future episode. So we're going to do the full little method here. So we draw the line, meaning we know we're somewhere on that line of longitude, and we've already drew the circle with the latitude. So where they cross is our exact location. But here's where it gets crazy. So I was showing other times, like I was doing the solstices and showing how the angles from a central location line up with the angles in SunCalc, and it's pretty neat. And I'm going along all the way down the longitude and showing no matter where we're at, it lines up. Like I said with SunCalc, but then I go to check some other locations. That's when I came across this discovery. Anybody who thinks that celestial navigation works perfect on a globe and SunCalc is exact with all the angles and everything, you are sadly mistaken. I'm going to show it right here. So I used negative 90 longitude for all the examples, and I used 30 latitude in all these. So here I have 30 latitude, negative 90. That lines up in New Orleans. Okay, and that's UTC -6. Okay, and I also used January, so there's no time change. Okay, so then you'd think that 0 longitude would be UTC 0, but it's +1. So 90 degrees away on the globe is +1. So I go to longitude -3, which is closer toward me, and I'm still at +1. So I'm checking into it. So I stay on latitude 30 and I go longitude -4 or -5, which means I'm 85 degrees away from where I started, and I'm still at +1. So I'm 7 time zones away at 85 degrees, and this gets ridiculous. So I put in 30 latitude and -6, so I'm 84 degrees away, and it's still 7 time zones away. So you'd think, that I would get to 0 pretty soon, but I wound up getting all the way to -11, and I'm still at +1. So I'm 79 degrees away, but I'm 7 time zones away, right? And this is all along the same latitude. Then I get to -12, and I'm -1. So I just skipped right over 0. I skipped right over 0. This is ridiculous. Then I go to -13, -14, and I think I get to what, -15 or so, and it jumps to 0. Like, it's anybody can make a model if this is how we're going to do it. So look right here. I'm 30 and I'm -12. Now it jumps to -1. You see that? -1. So I just skipped an entire time zone, which is crazy. So now I stay at latitude 30 and I go to -13 and I'm still at -1. So follow me here just for a second here. This is ridiculous, man. So 30 latitude, and now -15, which means I'm 75 degrees away from where I started. Now I hit 0. So, like I said, anybody can make a model. So now I'm going to have to just try and configure all this shit. But I had to show this because this is one of the bumps in the road that I've ran into, and I'm going to do my best to correct it. I don't think you have these problems on an AE map. You don't have to make these wonky freaking time zones with an AE map. And so here is -16, and it jumps back to, I'm 74 degrees away, and I'm at 0. Skipped right over 0 in the first place. It goes cuckoo, man. You can rewind and look at these numbers. Look, it goes from 0 back to -1. It just jumps. So I don't know. You be the judge. But I encourage you to go back and look at these numbers. So -24, I'm -1. How would I be 5 time zones away at that distance? It doesn't work on any level. Anyway, I'm gonna let it play out a little bit, but I went all the way to -22, which is 68 degrees away, and it's 0, so 6 time zones away, just 68 degrees away. It's crazy, man. I'm gonna do another video on this.